Hello everyone, I'm going to share with you our new measurement of muon neutrino disappearance using IceCube. IceCube can not only be used for astrophysics using high-energy neutrinos, but also be used to probe neutrino physics using low-energy neutrinos. Neutrinos raise many interesting questions themselves, such as why their masses are so tiny. What's the ordering of neutrino masses? Why does neutrino mixing look so different from quark mixing? What is their CP violation in lepton sector, which can help us to answer why the universe is dominated by matter instead of antimatter. Some of these questions can be answered by studying neutrino oscillations, which is a phenomenon describing that neutrinos created in one flavor later can be detected in a different flavor. There are three flavors, nu e, nu mu, nu tau, which are superpositions of the three neutrino mass states. Oscillations among the three neutrino flavors are described by the three mixing angles, a delta CP phase, and the squared mass differences of neutrinos. IceCube is sensitive to theta 23 and delta m squared 32 measurements by studying nu mu disappearance. If we write the nu mu survival probability, which is a function of oscillation parameters, and L over E, L represents the distance between the production and detection sites of neutrino, and E is the neutrino energy. To study nu mu disappearance, we use atmospheric muon neutrinos, which are produced by cosmic ray interacting with atmosphere. This gives us a neutrino dataset with wide ranges of both neutrino energy and their distance of travel. If we plot the survival probability as a 2D plot of distance of travel versus neutrino energy, we see these nice clear 2D oscillation patterns. The location of these straps tells us about delta m squared 32, and the brightness tells us about sine squared 2 theta 23. As you may have noticed, the biggest sensitivity is provided by this part of sample, which is a neutrino sample arrived through the Earth with energy between 5 and 100 GeV. So this is considered as low energy sample, and with the help of our sub-detector DeepCore, which is denser configured and using higher quantum efficiency dorms, we can actually see these sub-100 GeV neutrinos. We employ machine learning techniques which not only give us better reconstruction, but also is about 3,000 times faster in runtime than the current likelihood-based method. So here are the results contours. These are 90% confident levels assuming normal ordering. Our result, as in black, is compatible and complementary with the existing measurements in different colors. So we started by using very different neutrino sample in different energy range and also different distance of travel compared to the other experiments. But then we ended up we also facing very different systematics, but then we ended up a great agreement on the physics parameter measurement. And on top of that, we report one of the world's best measurement on delta m squared 32. So by looking at the 1 sigma error band, we see a very narrow error bar on this result. And we do expect lots of room for future improvement, especially with the upcoming upgrade detector. We hope to improve our detector calibration and also the event resolution. And we also have underway improved Monte Carlo models that can be applied to the future analysis. So here are my conclusions. This is the first time we use the highest statistic DeepCore atmospheric neutrino dataset, including the modern machine learning techniques to measure oscillation. parameters. We report a compatible and complementary result using with the existing measurements, including one of the world's best constraint on delta m squared 3.2. There's lots of room for future improvement, especially from our upcoming upgrade detector. And there are more results on the way using this new machine learning reconstructed sample, so stay tuned. Thank you.